All right, so in problem 3, we have that the power takeoff drive line on tractors used in agriculture is a potentially serious hazard to operators of farm equipment. The drive line is covered by a shield in new tractors, but for a variety of reasons, the shield is often missing on older tractors. Two types of shields are the bolt-on and the flip-up. It was believed that the bolt-on shield was perceived as a nuisance by the operators and deliberately removed. So they removed it on purpose. But the flip-up shield is easily lifted for inspection and maintenance and may be left in place. In a study initiated by the U.S. National Safety Council, random samples of older tractors with both types of shields were taken to see what proportion of shields were removed. Of 183 tractors designed to have bolt-on shields, 35 had been removed. Of the 136 tractors with flip-up shields, 15 were removed. We wish to perform a test of HO, our null hypothesis being that PB is equal to PF versus the alternative, PB is greater than PF. So basically the proportion of the bolt-on shields is equal to the proportion of the flip-up shields, and the alternative is saying that the proportion of the bolt-on shields is greater than the proportion of the flip-up shields. And we want to see, so the question is, which of the following is not a condition for performing the significance test? It's not a condition for performing the significance test. Okay, so remember the conditions are the random, 10%, and large counts. So let's see what we got here. Both populations are normally distributed. They don't have to be normally distributed. I mean, the answer should be yeah. It doesn't have to be normally distributed. This is like the way this gets taken care of is by the large counts. This is why we check if the number of successes and failures in each sample is at least 10. You know, if we have P times P hat times 1 minus P, or whoops, N times 1 minus P1 hat is greater than 10, and N, or N1 times P1 hat is at least 10, and the second one is N2 times 1 minus P2 hat is at least 10, and N2 times P hat 2 is at least 10. Checking the large counts conditions, having this large counts condition met allows us to use the normal distribution to make reasonable estimates for probabilities dealing with differences in proportions. And that's why the large counts condition is done. Like number of successes and failures for each group. So we don't need them both. We don't actually need them to both be normally distributed. So the answer is A. Let's just go through the rest just to clear up any questions you may have. The data come from 2 independent random samples. It doesn't have to be well, that is a condition. Well, actually, no, the rest, yeah, this is a condition. That's the random condition. That's condition 1. The data has to be kept to come from independent random samples. It's similar to that. They're different, but similar, meaning that the way, when we say independent, like, choosing an individual in one group is not going to affect your chances of the probability of choosing an individual in the other group. The probabilities of each group members is not going to be affected by one another. So that's basically B and C. So that D is what this is. So D is what this is doing. These values being at least 10 allows us to use normal calculations. And 10% is E. Yeah, so the answer is A. All right, problem 10.4. A quiz question gives random samples of size n equals 10 observations from each of 2 normally distributed populations. Tom uses a table of Tom uses a table of T distribution critical values and 9 degrees of freedom to calculate a 95% confidence interval for the difference in two population means. Janelle uses her calculator's two-sample T interval with 16.87 degrees of freedom to compute the 95% confidence interval. Assuming that both the students calculate the intervals correctly, which of the following is true? Okay, so before you even look at the answers, when you first learn about this stuff, you probably learn like this idea of being conservative. Like to get the actual degrees of freedom when running inference methods for differences in population means or population proportions, the degrees of freedom is actually is a very complicated formula. It's it's something you're not gonna have to worry about calculating by hand. Like the simple way to approximate it is just to use the bigger, it's use the smaller sample size, smaller of each sample, and then subtract 1 from it. Which if N1 is smaller, then use N1. If N2 is smaller, use N2. Now the smaller the less, or the smaller or the less the degrees of freedom is, the more conservative it's going to be, so the less wide it's going to be. Being conservative, we're talking about the confidence interval being less wide, because the less wide a confidence interval is, the more confident or the more certain you are that it's going to capture the values that it says it captures. It's going to be that it's truly going to be 90% in this 95% in this case confident. But when you use a calculator, this allows you to get a more precise confidence interval calculation, because then that allows it to become more wide. Because with the higher degrees of freedom, you're going to have a wider confidence interval, which gives a bigger range of values, because obviously you'll have more information about it. So the more conservative you are, or the smaller your degrees of freedom, the less wide it's going to be, given all other things equal. The bigger it is, the more wide it's going to be. So then going from that, Tom's is not going to be wider. Janelle is going to be wider. Janelle's confidence interval is going to be wider. And that's, the answer is just B. You don't need to know any other details, because it just says wider, and Janelle's is going to be wider. So the answer is B.